Today I'm going to present you a very little presentation about RPC threads, about RPC server calls, and how they are used in the wild for arbitrary function execution. So here, Atina already presented me, just a few words about me, and just a clarification about probably the LinkedIn post. Whoever saw the LinkedIn post, if you were waiting for this guy, I might have bad news for you. The guy ain't coming. I'm the one instead. I'm sorry, the cheap version. So I'm a managing consultant in BSI, head of research, where I in Business Standard Institute, where we do red teaming, pretty focusing now on hardware, embedded systems, medical device security, and code review. I'm a bug hunter, and if you check my LinkedIn, I'm Klets Virus, very inactive maintainer of a few tools. You can reach me out on Twitter or GitHub whenever you want. And all the code that I will present today will be available on my GitHub after the talk. So today we're gonna the agenda is we're gonna talk about a bit of basic about RPC, probably stuff that you've already seen, but just it helps to repeat. And then we will discuss about RPC server calls and how they are used in the wild and can be used in red teaming for code execution. And then I will show you two libraries, RpcCraft and RpcExec, that are a POC implementation of this technique. It's still in the early stages, but we're gonna make it more stable in the future. And then kavits limitation. I will also talk about what are the kavits, what are the limitations of these techniques, and what you should be careful about when using them. So RPC, you know RPC. RPC is an environment, is a infrastructure that is known as remote procedure calls. It's also known as DCE, and usually you refer to it as DCE RPC because you have distributed computer environment and remote procedure calls. Usually when you use RPC, there are a few phases involved with RPC, and you have a client and a server infrastructure, and what you do, you have an RPC client that will transform a message or are trying to invoke a functionality that is exposed in the server interfaces, and to do that, the client and the server usually implements a sort of interface which implements the way that this message gets passed to the server and gets interpreted and actually execute the wanted functionality. And the three kind of layers are ARMA shelling on the server side, the packet income, it's ARMA shelled, and it invokes a functionality on the server side that is relevant to what is defined in the message as the interface, the server interface that implements the functionality. Then there is the dispatching, of course. Usually in Windows, you use NDR server call, NDR server call 2, or NDR server call all. We will see them to dispatch to the core functionality as a dispatch table. And then you have an additional dispatch table that actually executes the API in Windows that you want to execute. And then there is a marshalling back because, of course, the response gets pre-marshalled in a network data representation format and get back to the client. And this is usually the flow. Of course, RPC can be implemented on additional protocols. Usually, we define this protocol as protocol sequence. Probably the most known protocol used for RPC communication is name pipes. And indeed, you have name pipes that can be specified when you connect, when you bind to a server. You can specify that the protocol sequence that you want to implement is the NCACN MP, which stands for name pipe. There are other kind of protocols that can be used for RPC invocation, for RPC binding, which are the TCP/IP protocol sequence, or the UDP datagram protocol sequence, or just the local procedure calls, that is, which one of the implementation is the lightweight remote procedure calls, which is a nice way to say that it's a sort of remote procedure calls that are optimized for local execution. And of course, you have also the HTTP, NCACN HTTP, that is actually HTTP based. Now, another important concept when you talk about RPC are binding handles. A binding handle is sort of an object that is never really fully exposed to the client. Is defined as an object that is available on server side, and it contains a lot of structures that can be used by the server to fetch and like take the state of the server, take the functionality, and redirect the functionality that is invoked by the client and achieve the correct result. Binding handles can be of 3 types, can be automatic, can be implicit, it can be explicit. And honestly, the only thing that actually changes is the amount of control that the client has on this binding handles. And you can see it very well in the next phase. So when there is an automatic binding, the servers define what is the correct binding for the client to select, and the client just select the binding exposed by the server and have no visibility on whatsoever. After binding is done, the binding stay the same for the entire conversation, client-server conversation. For an implicit binding, instead, the client actually sets the binding information in the packet, but then every functionality that is invoked on the server maintains the same binding. With an explicit handle, instead, every functionality invoked by the client needs to have a binding handle associated to that. So the client can specify for every call that he wants to execute, can specify the binding handle associated to it. Another concept about RPC endpoint, of course, an RPC server acts as a regular server. So in a nutshell, everyone can actually interact with it and potentially execute code and execute the exposed interface. The interface is exposed by the server. Now, in order to protect this kind of service, you can use like well-defined techniques. One of these are the registration flags that have to be specified during the initial binding with the server, and literally are just predefined flags that you can use. Like, for example, you can restrict the binding to be performed only locally, or there are others. And then you have a security callback that offer a kind of more granular approach to this same concept. So whenever a client is attempting a binding, there is a security callback that can be triggered. It will check on information passed by the client and check if the client can actually connect or not to the server. And then you have another layer, which is literally authentication. And in these cases, when a client tries to bind to a server, the client needs to specify credentials to authenticate to the server. And if it doesn't pass the credential check, it won't be able to invoke any functionality from the server. Now, in this context, there are what we call RPC server calls. And what are RPC server calls? RPC server calls are what you can find in, like, the whole environment of RPC is actually present in a single DLL of Windows. It's actually I'm abusing here a bit, but like the most of the functionality exposed by the runtime of RPC is RpcRT4 DLL on Windows, and there are many functions that can be defined as server calls. What I mean with server calls is all the functions that actually execute at the network layer after a packet has been received and unmarshalled. Every RPC packet will contain, in the end, after unmarshalling, will contain an RPC message that will contain all the details around what interface was invoked and with what parameters, etc. Now, the invocation usually goes like this. A packet is unmarshalled and then is passed to NDR server call 2. NDR functions, like in RpcRT4, there are mostly three kinds of functions. There are RPC functions that are literally related to the RPC runtime. That are I_ functions that are actually wrappers for specific interface implementation of functions. So are like dispatcher for wrappers for this kind of implementations. And then there are NDR calls that are all calls that operate at the network data representation level. So NDR server call 2, which is synchronous, and the other two that actually should act as thread invoker, so NDR server call all and NDR server call NDR64 are like supposed to be asynchronous, all dispatch into other functions. And for example, NDR server call 2 dispatch to NDR stub call 2 that ultimately call the invoke functionality. Now, the execution sequence flows like this. You have NDR server call 2 that calls the stub call 2 that ultimately calls the invoke function after a lot of checks on the RPC message, and ultimately calls with a cop gadget call R10 invoke a functionality, which is a function, an API, better, a dispatch table that is specified in the RPC message. Now, why we care about this is because there is actually abuse in the wild of this technique. So you can recognize it's not American APT. So Chinese APTs are actually using this. It's in a complex chain, so not just RPC invocation, but a lot more. So in this case, they were using, they were triggering a number shelling of an RPC message through through a function that was freeing a message on a pipe, and they were literally posting stuff on a pipe using, and they were using also this in a combination with a well-known exploitation trick that is used to abuse this tag-wind and then tag class to allocate shellcode in the kernel. Actually, not really in the kernel, but they were using it to allocate shellcode abusing the GUI system of Windows. So they were like literally adding tags to GUI to Windows using the Win32U DLL. And then we're abusing this RPC call. As you can see, there is this server call all. They were using this trick to trigger the functionality, so the shellcode that they allocated in that way using the GUI subsystem of Windows to execute their own shellcode. And as you can see, there is also the concept is really the same. They're using a pipe, they're releasing a pipe buffer that triggers the execution of the shellcode via NDR server call all. And NDR server call all is literally what I was saying before. Instead of calling NDR stub call 2, it uses NDR 64 stub worker, which is supposed to execute in a thread as a thread worker, but it's the same concept. So now, using this same strategy, we try to poke out a way to execute arbitrary functions in Windows ourselves. And we call this RpcCraft and RpcExec. They are the same thing. RpcCraft is local, RpcExec is on remote processes. Now, all starts with a message. We just said that this thing is all implemented using just an RPC message. Now, the RPC message structure is appearing like that. As you can see, is a pretty rich structure, and honestly gets even more complex than this. Something that we want to, some concept that we already aligned that should be familiar now are the binding handle, which is the first one that gets specified. And this is a binding handle, of course, not a context handle, but then we have the buffer that will ultimately contain the parameters that are specified as part of the routine that needs to be invoked. And then, of course, you have the interface information that contains the information about the interface, so the functionality that supposedly the client is trying to invoke. Now, based on a research, very old research of a browser exploitation technique, we actually managed to understand what was the potential RPC message structure. So we actually saw the research, we tried to replicate it a bit, but it was not complete. So let's see what we need to make this work. So first thing, we dissect this RPC message structure. As we say before, we need the RPC interface information, and we can select two kinds of information, server interface, client interface. So the size of this interface is literally the same, and mostly the parameters that we need to fill are also kind of the same, they are overlap. So you can literally select one of the two. We opted with the client interface just because we are acting as a client, even if we are executing a server functionality. But that literally doesn't have any difference. You can select one of the two. As part of this, you see that like there should be like a pointer to a middle class, which is so important stuff. So the dispatch table here, we don't need to worry about this because usually this is done at AMR shelling level. So this dispatch table usually contain a pointer to NDR server call to, NDR server call all, because this is actually telling the server to execute this interface, you need to dispatch using this dispatch table. So usually that just contains the dispatch function. Because we are already executing the dispatch function, which is NDR server call to, we don't need to worry about this too much. As part of this, we also need a pointer, a valid pointer to the middle server info. The middle is the middle compiler, is usually what you use if you try to create a client-server infrastructure in RPC. You will need to use at a certain point the middle compiler that will compile actually your classes following the RPC, the RPC standard. And as part of this, we see there are a few fields. What we care about in this specific structure is the dispatch table. It's not the same as before. The dispatch table before was the dispatch layer, so how I dispatch this to the right interface. This dispatch table here instead is, okay, I dispatch it to the correct server. Now, what is the function in that specific server that I want to execute? And this will contain the API I want to execute. And here we see also the format string. Now, the format string, you don't think it's relevant. It's actually fundamental because it will, as you remember before, we pass all parameters as a buffer. Now, how the server can understand how to parse that buffer and fill the right arguments, this is what you need. So the proc string will actually tell the server, take this buffer, take this proc string, this is how you interpret it. Now, it's not a format string like printf style proc string. It's a bit different, but we will get to that. And then we need a valid middle stub description. So the middle stub description is pretty darn complex, but luckily enough for us, this defines a lot of routines that are usually used in a fully implemented RPC server implementation. But what we actually need is not really a lot of things. We just need this to be a valid pointer. It can be a pointer to null. We don't care. And we need this to be populated if we want to pass some checks later on in the buffer. And these actually are just a pointer to malloc and a pointer to free. It should be pretty easy to make. And now, coming back to the proc string, which is the most important part, because as we said, we need to understand how to parse the parameters, how we actually do it. So this is how it's usually a proc string is defined. It looks very scary. In reality, is not that scary. This part is pretty much fixed. The only thing you need is actually this. Oh, I have it this time. The thing that you actually need is that, because it's defined the stack size. So all these parameters are actually passed on the stack dynamically. So in order to pass all the parameters that you need to define a stack size, which is, well, the number of parameters per 8, because every parameter is 8 bytes in size. This is not always the case, to be fair. It's just a simplification that we use because, I mean, we may have a lot of different functions to use, so it's better to just specify that every parameter is 8 because it's the maximum size that we would use anyway. And this flag is important because it will define that our function has a return address. And then we need this value, which will be the number of parameters plus 1, and the plus 1 is to account for the return value. And now the input parameter definition is, well, for any input parameter which is defined in RPC as an FC hyperparameter, which has this flag, this is fixed, you will need to just specify the stack offset. So of course, for every parameter, the first one will be 8, the second one will, so the first one is 0, the second one will be 8, the third one 10, and so on, to fill out the stack. And for the return value definition, instead, the flag is not 48, is 70. The second is the stack position, which will be number of parameters per 8 plus 8, pretty much. And this and the is still an FC hyper, and then we end up with a 0. So just to avoid the struggle, I just have a script to generate the proc string. You can find it on my gist. It just saves a lot of time. You just specify the number of parameters that you want to have, and it just generates it for you to account for stack size, etc. It's very simple script, but you can adapt to your own needs. And this is the final mesh abstractor that we actually came up with, and it's working pretty fine. We still have some problem. As you see, the proc string is there. For this POC, we account for like 14 parameters just to define every possible API that we wanted to invoke. But we still have a crash. So it was not like after we did all this implementation, we ended up with a crash that is showing in the NDR stub call 2, and if you can see, it's actually happening during allocation. So we wondered, I mean, we put an allocator, so you should be able to find an allocation, why it's crashing. So if we define, we see that RpcRT4 actually on initialization, so when initialize a client or a server counterpart, it initializes a lot of variables, global variables. So for example, one of these is the pointer to the heap. It also have an LSA alloc and other stuff that is used currently, that is used like in general during, so you can see there, LSA alloc. And these are all variables that gets usually populated at startup when I set up a server or I do an initial binding. So we said, how we address for this? Because this is empty. So this is a pointer to the heap, should be a pointer to a heap, but it's empty. So when it's tried to allocate on the heap, it just crashes. It's natural. We didn't have any initialization because we are doing this without any binding, without binding to any server. So, but we don't want to bind to a server. We just want to execute. We don't want to bind. So reversing the binding, so this is usually one of the functions that you use during binding is RPC binding from string binding A. And we find that there is a very interesting function there, which is perform RPC initialization. So we said, well, what if we find this function and we manually initialize it, we manually fire it. It doesn't take any argument, so it's very convenient. And well, I didn't put it here, but it works. So initializing, doing the perform RPC initialization before actually trying to execute any server call works. But there is still something to fix. So because we missed the binding handle, which is a very important information in a client-server infrastructure, we still have an exception being raised after we invoked the functionality. And this is caused by NDR get buffer that internally calls IRPC get buffer with object. Now, as you can see from the reverse code, this actually takes only the handle, the binding handle as variable parameter. So the binding handle is a pointer to a structure that is available server-side. So the correct way to handle this would be to actually provide a fake or reuse another handle that is correct for this specific case in order for it to pass all the checks. Now, this is still ongoing as a research. The ideal solution would be this, just trying to craft a completely fake handle that passes all the possible checks. But we tried also to use the original handle that was used before in the research that I showed you before, in the browser exploitation research. But of course, that doesn't really work. It doesn't work because that was tied to a RPC server tied to a browser. So passing the same pointer would be probably not the right strategy. I mean, we tried it, but it didn't work. So we're still working on this part. But in the meantime, what can we do to actually execute stuff? Well, first thing would be a try except. We just get the exception. We just call it a day. The function triggers correctly. We don't care about what happens afterward. Well, yes, but we don't have any return. We don't have any return value like this. So the very easy peasy strategy to do with this is just to use a very well-known technique, very well-abused technique, over-abused technique, which is vector exception handlers. We combine this regular C++ style exception with an exception handler that just fetches the exception, just save the return value in a global, and just return it to us. And this works, by the way. This works perfectly, of course. It was expected. But what about executing remote calls? Well, remote calls are another story because we don't, unless we are loading a DLL in memory and we can actually set up the vector exception handler, well, it's going to be tough. It's going to be tough to have the return value back, at least. But there are other things to actually care about. So if you see the invoke functionality, it has a RPC invoke check ICall. Now, that RPC invoke check ICall can be a showstopper because it's the implementation of CFG RPC side. So that call will actually contains an invocation of the check guard ICall pointer that will actually check the CFG bitmap before executing the function that we specify in our RPC message. So, well, what can we do? Well, I mean, the only solution would be either, well, there are two solutions actually, or either we set as valid call target using set process valid call target API, we set as valid CFG target the function that we want to invoke, and we do it for every function that is protected by CFG, that is restricted by CFG, or either we just patch this function. Well, we selected the patch because it's easier and it's global. And as remote initialization, of course, we also need to be aware that the initialization, so we injecting in Notepad is not going to have an RPC server listening, so we need to initialize RPC, as I told you, in the local case. And we also have another problem about catching the exception. What can we do with the exception? If we cannot install directly a vector exception handler, and surely it doesn't matter if we do a try except. So the easiest strategy possible is, in this case, to patch the exception, so the RPC raise exception, to redirect to a thread exit, because we will execute as create remote thread whenever an RPC exception is raised. Instead of raising the exception, we just redirect to thread exit, and that will prevent a crash in the remote process. So in order to patch thread exit, so the patching to RPC raise exception is fundamental, and probably the best way to do it is in RPC-P raise exception, which is the real implementation of the raise exception RPC side. And patching this function would be ideal probably because we have also the possibility in this function to have an ETW event being written as an ETW provider, and this is something we would like to avoid in general, ETW. But patching this, of course, will have we will discuss about what are the impact of overriding this function, but this would be the ideal way. So here we will just locate exit thread and jump to exit thread and override this function. Another approach would be patching raise exception. I mean, we can still nullify this Microsoft Windows RCP enabled bits, and we can patch raise exception. Raise exception is a function that is part of the many APIs loaded in Windows. It is an import that is imported by this function, and you can see there, raise exception 7. So we can locate the DLLs loaded in the process. We can locate the import address table of this API and just patch this import address table so that it points to exit thread. This is a bit more stealthy than the other approach, but they both work fine. For CFG, we have another problem by itself, because the function that is known as RpcCheckICall is not really exported, so we need a way to find it. And the best way to find it that we found is, in all RPC, there is just a cop gadget, which is call R10. So what we do is this. We hunt for cop instructions, and we select the cop R10, so the call R10. After we locate the cop instruction, what we do is we hunt for a call instruction, which is preceding the call R10 instruction. Just if this is not clear why, let me go back a second, because this is kind. So because, as you can see here, we have an RPC invoke check I call, and then the first call before, sorry, we have the, yes, we have the invoke function, what it is? It's this one. So this is a call R10, and the call just before that is RPCI invoke check. So what we do is that we try to find this call R10, and then we go backward until we found a call. And this is the strategy, literally, and we are here. So when we found the call, we need to also locate where the address is going. So we calculate the address, the real address, and this is the formula to calculate the real address. And then we have a way to actually understand where this function is. Once we have it, we just simply patch it with a ret. So whenever it goes there, just goes back. The return is 0, everything is good. Because this function doesn't actually return anything. This function just generates an exception when the target is not in CFG. So just putting a ret is fine. So we have our operation sequence. We need to find the RPC initialization routine. We trigger it. We patch RPC raise exception. We find and patch the RPC invoke check I call. We craft our RPC message, we execute. This is the operation sequence, and we have it here in the local case. I don't have a real demo, I'm sorry for that, but this is in the local case. We are crafting message box as very great hacker do. Message box, and then in the remote case, we have Notepad running here. We locate Notepad, and we do exactly what I said before. The only thing you need to understand here is that we are allocating memory on the remote process. It's not executable memory. So the advantage is you don't need executable memory. You just allocate RW memory, and you can execute with arbitrary parameter, because you still need to have the parameter somewhere. So not the parameters, the message. We still need to have the RPC message being accessible to the remote process. So you still need to allocate some RW memory on the remote process. But you don't have the stigma of executable memory. And so key takeaways. So this technique can be used to, well, not really to fake the call stack, but it's just an alternative. When you execute something, instead of executing it directly, you execute it pretending to be an RPC server. And this can help masquerading some sort of detection that is based on the call stack, because you will have a call stack that is not the expected call stack. You can execute in remote thread, so I'm pretty sure if you are in red teaming, I'm pretty sure a lot of you are using the trick of anti-continue. So practically, when you want to execute a function on a remote process, you craft a context structure, then you find a trampoline on the remote process that jumps to a register where you have put anti-continue. And this is the usual way you actually you execute arbitrary code in a remote process without Rx memory. This is an alternative. It's better, it's worse. If we can stabilize the RPC message so that it doesn't trigger any exception and we can avoid all the other stuff, it's probably be even better than anti-continue, because it's very strange to start a thread with anti-continue, although I don't see it very often scrutinized. And then ultimately, this can be used as a sort of framework to implement a sort of railgun style stuff. If you don't know Railgun, Railgun is a library from Metasploit, and literally when you have an implant running, you can specify an API and parameters, and it will execute it for you. And this kind of RPC infrastructure can be abused for implementing exactly the same thing, but just with RPC. And in terms of detection, of course, there are a lot of, this technique offers, I mean, currently is not really heavily detected. I would say it's not detected at all, but just because it's not very known. But I mean, of course, there are a lot of places where you can actually enter detection for this, because now we are patching stuff, so we are patching RPC. You will have private bytes appearing in RpcRT4. So there are chances for detection, especially if you are actually trying to do it in a remote process. If you're trying to load it as a DLL or you're doing it locally, well, then the only chance for detection is actually the handler, the VH. If you remove that, there's no way to actually hunt for the technique. Then what you do with the technique, what you execute for the technique is your style. If you execute shellcode, then of course it depends on the shellcode. And that concludes the presentation. Thanks a lot for listening to me.